Bismillahirrahmanirrahim. Assalamu alaikum. Functional analysis, code math 424. My topic minimizing vector theorem. Statement of theorem. Minimizing vector theorem statement is this: let X be in inner product space and M not equal to empty, a convex subset which is complete in the metric induced by in the inner product. Then for every given X belong to X means X belong to X not belong to M, there exists a unique Y belong to M such that delta is equal to infimum norm of X minus Y prime, Y belong to M, Y prime belong to M is equal to norm of X minus Y. Equation 3. Proof. First we existence of the theorem. First part existence. Existence by definition of an infimum, there is a sequence yn in M such that delta n approach to delta where delta n is equal to norm of X minus Y n. Equation 4. We show that yn is Cauchy. Written yn minus X is equal to Vn. Similarly, ym minus X is equal to Vm. We have norm of Vn is equal to delta n. Similarly, norm of Vm is equal to delta m, and norm of Vn plus Vm is equal to yn plus ym minus 2x, means Vn is equal to, above this is Vn is equal to yn minus x put here, and also Vm is also put here ym minus x, yn plus ym minus x minus 2x is equal to 2 into norm of 1/2 yn plus ym minus x. We are taking common 2 is greater or equal to 2 delta. We know that this one is greater or equal to 2 delta because this one is equal to delta, because M is convex, so that 1/2 into yn plus ym also belong to M, yn belong to M, ym also belong to M, both sum are also belong to M. 1/2 also constant, multiply then also belong to M. Furthermore, we have yn minus ym is equal to Vn minus Vm. Hence, by the parallelogram equality, we know that by the parallelogram equality is norm of yn minus ym whole square is equal to norm of Vn minus Vm whole square is equal to minus norm of Vn plus Vm whole square plus 2 into norm of Vn whole square plus norm of Vm whole square less than or equal to minus 2 delta whole square, means this one is equal to delta. Here the above this one is, we know that Vm plus Vm, Vn here Vn plus Vm also greater or equal to delta. To write this portion term is right is this one 2 delta whole square plus 2 into this one. We know that here Vn norm of Vn is equal to delta n, here Vn norm of Vn is equal to delta n square, and यहाँ this one square plus Vm also norm of Vm delta m, यहाँ delta m whole square. So existence is clear. Now the second part of, we show that the uniqueness of the theorem, we assume that we assume that y belong to M and y not belong to M, both satisfy. Uniqueness means y and y naught are equal. We show that y is equal to y naught. Just norm of x minus y is equal to delta, and also x minus y naught, norm of x minus y naught is equal to delta, and we show that then y naught equal to y. This is show that my required point is this one, y naught is equal to y, then y is a uniqueness. So by the parallelogram equality, norm of y minus y naught whole square is equal to y minus x minus y naught minus x whole square. We add and subtract x, then we write in this form. So is this one is equal to, by using parallelogram equality, is equal to 2 into norm of y minus x whole square plus 2 into norm of y naught minus x whole square minus norm of y minus x plus y naught minus x whole square is equal to 2 to this one 2, this one is equal to delta, so norm of y minus x delta square whole square, so this one delta square plus 2 is here and this one is also here above delta, this one is equal to delta and also this one is equal to delta, so we put the value of this and minus here using parallelogram equality, so minus 2 square norm of 1 by 2 into y plus y naught minus x whole square. On the right, 1 over 2 into y plus y naught belong to M, so that norm of 1 over 2 into y plus y naught minus x greater or equal to delta. This implies that this norm of 1 over 2 into y plus y naught minus x greater or equal to delta. This implies that the right hand side is less than, the right hand side is less than or equal to 2 delta square plus 2 delta square minus 4 delta square equal to 0. 2 delta square plus 2 delta square 4 delta square, 4 delta square minus 4 delta square is equal to 0. Hence we have the inequality norm of y minus y naught less than or equal to 0. Clearly this one, norm of y minus y naught norm less than or equal to 0, so clearly y minus norm of y minus y naught greater or equal to 0, so that we must have equality. This one is less than or equal to 0, this one is greater or equal to 0, so that we must have equality and y naught is equal to y. This is my required point, so the uniqueness is shown. So turning from arbitrary convex sets to subspaces, we obtain a lemma which generalizes the familiar idea of elementary geometry, that the unique point y in a given subspace y closest to this one, that the unique point y in a given subspace y closest to a given x is found by dropping a perpendicular from x to y. Goodbye.